What's up, guys? It's Mr. Brengle, and today we're going to be talking about wave speed math. And the good news is that this is pretty simple, and we've got one equation really that we're going to be using here. A couple equations, but main equation is right here for us. So wave speed, which is still a v. Okay, wave speed is equal to wavelength, which is a new symbol. This is a upside down y of sorts. It's called lambda, Greek letter lambda, and that represents wavelength. And wavelength is going to be measured in, meters, centimeters, nanometers. It is a length, so it is meters. And then frequency, which is lowercase f, which we've talked about, and that's going to be measured in hertz. A couple things to note here. The speed of sound is going to be accepted as 340 meters per second, and the speed of light is going to be 3 times 10 to the 8 meters per second, which is 300 million meters per second. So you'll want to keep those numbers in mind there. All right, so as we scroll down here, in this first example that we're going to jump into here, we actually need this conversion that they've given us here. It says that I apologize, let me get my, it says that 1 megahertz is equal to 1 times 10 to the 6th hertz. And then in this question, it says radio station WCRB in Boston broadcasts at a frequency of 99.5 megahertz. What is the wavelength of the radio waves that are emitted by WCRB? So here, let's go ahead and write down what we've been given. In this case, it gave us the frequency, which is 99.5 megahertz. We're going to need to convert that to just plain hertz. And then it does want to know what is the wavelength, but it doesn't tell us anything else. Now, based on that equation that we had, wave speed is equal to wavelength times frequency. We're missing the wave speed. Well, radio waves are an electromagnetic wave, which are on the same spectrum as light, so they are going to travel at the speed of light. So the speed here is going to be 3 times 10 to the 8 meters per second. Okay, that's our speed of light here. Okay, now we, of course, the first step here, we need to actually, I'm going to go ahead and erase this. We actually need to convert 99.5 megahertz to just hertz. So if we're going to do that, 99.5 megahertz, I like using the chemistry style conversion here with the fractions. 1 megahertz on the bottom here, so that this way the megahertz cancel out. And then 1 megahertz is equal to 1 times 10 to the 6 hertz. Okay. So all we're going to do is multiply 99.5 times 1 times 10 to the 6. And make sure you're using the exponent button on your calculator. So 1 exponent 6. And this is going to give us 99,500,000. So let's go ahead and write that as 99.5 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6. Which makes sense. I'm not sure why I needed to count that out. So instead of using 99.5 megahertz, we're going to use 99.5 times 10 to the 6 hertz. And now we can use our equation. So remember the original equation, wave speed is equal to wavelength times frequency. We're going to rearrange this for wavelength. So what we need to do is we need to divide by frequency on each side. So these will cancel out. And what we're going to be left with is that wavelength is equal to wave speed divided by wave frequency. And then we know that our wave speed is 3 times 10 to the 8 meters per second divided by 99.5 times 10 to the 6 hertz. Okay, so we'll do 3 exponent 8 divided by 99.5 times 10 to the 6. And that's going to give us a wavelength of 3.02 when you round. meters. Okay, so we'll go ahead and move on to the next page here, and we'll move on to example 2. Zoom in a little bit. So this says that California Clay is surfing on a wave that propels him toward the beach with a speed of 5 meters per second. So we'll go ahead and underline that. Wave crests are 20 meters apart. So what that's telling us is the wavelength, because it's telling us that the crests are 20 meters apart. Remember, wavelength is distance between two identical parts on a wave. So crest to crest would be one wavelength. This wants to know what is the frequency of the water wave and what is the period. So here we've got wave speed is equal to 5 meters per second. We know that wavelength is equal to 20 meters. It wants to know what is the frequency, and then also what is the period. Now, once we solve for frequency, we can easily figure out what period is. So we'll do that first. We'll solve for part A first, and then we'll move on to part B. So for this, again, our equation is wave speed is equal to wavelength times frequency. So since we're solving for frequency, we need to divide by wavelength on each side to get that off of this side. So this will cancel out. We can now see that frequency is equal to wave speed divided by wavelength. Okay, so let's go ahead and calculate that. Frequency is equal to 5 meters per second divided by 20 meters. So your frequency here is going to be 0.2 hertz. Okay, so there's part A. And then for part B, just remember that you're going to want to use the reciprocal calculations. Remember, frequency is equal to 1 over period. I'm just going to write these out over here. 1 over period. And then period is equal to 1 over frequency. Okay. And let me add in 0.25 hertz there for the frequency. Okay, now coming back to this here, period, since it's equal to 1 over frequency, it's going to be 1 over 0.25 hertz. And therefore, period is going to be equal to 4 seconds. Because remember, we measure period in seconds. It's a measurement of time. So another way to write hertz, another way to write this would be 1 over a second. So you could theoretically, like another way to write this calculation would be 1 over 4, right? 0.25 is 1 over 4, and then the units are 1 over a second. So when you multiply by the reciprocal, it ends up being, you do times 4 seconds, right? So we flip this fraction, so now the 4 and the 4 cancel here, the seconds and the seconds cancel, multiply by 4 seconds, and that's what we end up getting, right? So anyway, we'll go ahead and move on to the exercises here. So those were the examples, and then I am going to do, 1 or 2 of the exercises, and then I'll have you guys finish them. There are 4 total exercises, and I'll go ahead and do this first one because it's a little bit, just a little bit different. Okay, so it says that Harriet's told by her doctor that her heart rate is 70 beats per minute. Okay, so that's like cycles per second. So remember, if we're talking about frequency, it's the number of cycles, in this case beats, per some unit time, in this case minutes. So beats per minute is a frequency. We'll go ahead and put that over here. So 70, I'm going to put, okay, we'll just write beat over minute. Okay. If Harriet's average blood flow in the aorta during systole is 1.5 times 10 to the negative 2 meters per second, so another way to write that would be 0.015 meters per second. So whatever you feel more comfortable with on that. And then it says, what is the wavelength? So we will solve for that. And again, our equation that we want to use here is wavelength times frequency is equal to wave speed. We need to rearrange for wavelength, so we're going to divide by frequency on each side. We find that our wavelength is going to be equal to wave speed over frequency. And then we can actually just go ahead and plug that in. So I'll rewrite this as 0.015 meters per second. So remember to change scientific notation into a decimal. We had 1.5 times 10 to the negative 2. So the decimal was originally right here, and then we moved it 2 spots to the left to get 0.015 meters per second. Okay, so that is 0.015 meters per second divided by 70 beats per minute. But now we're looking at this and we're saying, oh, wait a minute, that doesn't match up, right? We've got meters per second and we've got beats per minute. So ultimately what we need to do here is we need to convert 70 beats per minute to beats per second. And that will help us out here. So let's go ahead and do that. So 70 beats per minute. And then I know that in 1 minute, there are 60 seconds, right? So we'll do this, and these minutes are going to cancel out. So 70 divided by 60 will give us 70 beats per second. So this comes out to be 1.16 repeating. This would be beats per second. Okay, beats per second. So we'll go ahead and we will erase this. We'll go ahead and put in 1.16 beats per second. Okay. Okay. So now we'll go ahead and do our division here. So 0.015 divided by that number. I left it in my calculator, didn't round. And then I end up getting a wavelength here of 0.013 meters when you round. Okay. So what that's saying is it's a wavelength of 0.013 meters from beat to beat, or the crest to crest on the wave, equal parts of the wave. And so that'll be your first answer there. Okay. Now, the second problem, I'm going to go ahead and let you guys do that one on your own. I think that you can handle that. The one thing I will say here is that the only thing it gives you, it says there's a frequency of 3 times 10 to the 4th hertz. It wants to know what is the wavelength. You are missing the speed. And since this is a dog whistle, it's going to be traveling at the speed of sound. So it gave it to us at the beginning of the assignment. It's up at the top. But we're going to use, so speed of sound is 340 meters per second. That's a constant. So you'll use that for that problem. Moving on to the next page here. Example 3. This says that she's on a plane and the turbulence causes her coffee cup to oscillate back and forth 4 times each second. So that right there is going to be your frequency. It's 4 oscillations per second, or 4 cycles per second. So okay, 4 cycles per second. If the wave If the waves of coffee have a wavelength of 0.1 meters, what is the speed? So you have the wavelength, you have the frequency. You'll solve for the wave speed. I'll let you guys do that. And then in this last problem here, it says that at a country music festival, they're playing at the end of a crowded 184-meter field when Ronnie Fairchild hits a note on a keyboard that has a frequency of 400 hertz. Okay, so imagine, so there's a stage right here. It's 184 meters to the back over here. Okay, and there's sound coming from up there. All right, frequency of 400 hertz. So we'll go ahead and write that in. How many full wavelengths are there between the stage and the last row of the crowd? So we're looking for wavelength here. In fact, what we're going to have to do is we're going to have to figure out what one wavelength is and then figure out how many full wavelengths there are in 184 meters. So we'll get to that. And then it says how much is the delay, the time between when the note is played and when they hear it at the back. So we're also looking for time here, which we can solve for. So the big thing here is that we need to know that the speed of sound is 340 meters per second because they're playing music. We're solving for wavelength. So wave speed is equal to wavelength times frequency. We're going to get frequency off of this side. So we're going to solve using wavelength is equal to wave speed divided by frequency, which is going to be 340 meters per second divided by 400 hertz, which is going to give us a wavelength of 0.85 meters. Okay, so that's one wavelength. This is one wavelength. What this question asked us for is how many full wavelengths are there from the stage to the end? Right? So there's 184 meters. So what we'll do here is we'll take 184. So this is part A. 184 meters divided by 0.85 meters because that's the length of one wavelength. And that's going to give us 216.47. So since it asked for full wavelengths, it's just 216 wavelengths. Okay, 216 wavelengths. Okay. Now for part B, what we could do here is figure out the time for, we could figure out period, figure out the time it takes for one wavelength, multiply it by the number of wavelengths. Alternatively, you could also just use that speed is equal to distance divided by time. We know the wave speed, we know the distance, we can solve for the time. So if we were going to get time by itself, we would multiply by time on each side. Now we have distance is equal to TV. We divide by the speed on each side, and we find that the time will be equal to distance divided by speed. So what we'll do here, time is equal to 184 meters divided by the speed of 340 meters per second. That's the speed of sound in air. And then we find out that the time is 0.54 seconds. And that's how much time it takes for the sound to travel from the stage to the back, the people that are in the very back there. Okay. All right. So there are your wave speed examples and exercises. Make sure to complete all of them. I've obviously worked some of them out, left a couple for you to do on your own. Let me know if you have any questions.